if we have an object accelerating down an incline, then the object is going to lose gravitational potential energy. Remember that the gravitational potential energy difference between here and here is the work that would be required to lift the object from here to here, or alternatively to push it up the incline in the absence of friction. If the vertical distance between this position and this is delta h, and forgive the sloping line, when I drew it I was at a bad position and it's really pretty bad here, but if the delta h represents the difference in vertical position here, then the work required to raise the object is its weight, which is mg, times the distance, which is delta h. Notice that the weight is going to be in the same direction. Notice that the force required to raise the object will be in the same direction as the delta h, opposite to the direction of gravity. Now, if we release this object from rest, we could, in an experimental situation, find delta t. Okay, if V0 is 0 and we have delta t and delta s, we can easily find then the final velocity. Okay, by measuring delta t, and we have the sufficient information to find the final velocity of the object. And what we're talking about here is how we could test the conservation of energy in this situation. Okay, so ideally what should happen then is we're going to have a change of kinetic energy, of course, that we can calculate from Vf. Since V0 is 0, that's just going to be 1/2 mVf squared. And we test whether the change in kinetic plus the change in potential energy is indeed 0. Now the change in potential energy again is going to be our mg delta h, and it's going to be negative. As we go down, the potential energy decreases. So that the change in kinetic 1/2 mv squared and the change in potential negative mg delta h add up to 0, and we can easily test this to see whether this is indeed the case. Now the question was raised, how do we show that the work done in pushing the object up here is equal to the change in potential energy mg delta h? Well, if we push the object a distance delta s up the incline, and the incline has angle theta, then our delta h is going to be delta s times the sine of theta. That's just by simple trigonometry. The delta w that we get if we push the object up the incline, on the other hand, we can take our weight and break it into two components, mg cosine theta and mg sine theta here. And we're going to be pushing against the weight, or the force, mg sine theta, the weight component down the incline. The work that we do is then going to be mg sine theta times delta s. Now, from what we said before, delta h divided by delta s is the sine of theta. That's the opposite side over the hypotenuse of this triangle, if we assume that the distance here is delta s. It's not been very well labeled, but I hope you can see what I mean. So if we replace sine theta by delta h over delta s, then when we multiply by delta s is multiply out, and we end up with mg delta h, and that is indeed our change in potential energy, the mg delta h that we talked about before. So by assuming an angle theta and a delta s up the angle, we find that the work we do in pushing the object up the incline in the absence of friction is indeed equal to the change in potential energy.